MEMS fabrication. So the micro machining or microfabrication actually consists of four separate areas, and these are substrates and dopants, which is actually the starting point. So normally we start the microfabrication or micro machining or the fabrication of MEMS with a substrate. And generally, in a lot of occasions, silicon is used as a substrate. And we add dopants in order to make the substrate P-type or N-type. So dopants are added depending upon the requirement of the device. After that, we have patterning. Patterning means we transfer the shapes, we transfer the patterns from the mask onto the substrate. And that technique, which is used to transfer the surfaces or shapes or features onto the substrate, it is known as lithography. So with the photolithography, normally we transfer the features from the mask onto the substrate. And then we have additive processes. By additive processes, we add layers to the substrate. Remember that MEMS fabrication is layer by layer fabrication. We fabricate the device layer by layer. We add the layer and then we do etching, and then we add another layer and do etching. So we add the additive processes, and in the additive processes is deposition of material, deposition of thin layers of material, and then we have a subtractive process, which is etching. We do etching of the layer which is added to substrate layer. To be more precise, we are doing selective etching. Some area of the surface which is added to the substrate, it is etched with the acid or strong base. So the process is known as etching. So these are the four main areas or processes by which we could do the MEMS fabrication. So substrate and dopants, which is the starting point, then we do patterning with the lithography. We add layers to the substrate with the deposition process, and then we make the desired shape on the deposited thin film with the etching process. We are actually combining lithography with substrates and dopants, additive process, subtractive process, and at the end, the result is micro machining. So all these steps are known as micro machining. These are it is called micro machining or microfabrication. So micro machining combines lithography. Lithography is the process by which we transfer the patterns or features from the mask into the substrate. Thin film processes. Thin film processes is the deposition of material on the substrate. And sacrificial etching. Sacrificial etching means selective etching. So some portion of the added layers are etched with the help of the etchant solution. And by that way we form the mechanical devices which are called MEMS devices. So normally there are three types of fabrication processes that are involved with the MEMS fabrication. Number one is the surface micromachining, bulk micromachining, and microforming. Surface micromachining is the process in which we fabricate the structures on the surface of the silicon wafer. In this process, we make structures or features on the surface of the wafer. Bulk micromachining is the process in which we make structures within the silicon wafer. So here, layer by layer, we make structures on the surface of the wafer, while here, in bulk micromachining, the structure is made within the silicon wafer. The same silicon wafer material is used to make this structure. And then we have microforming. In the microforming, we use electroplating, molding and electroplating to form structures on the surface of the wafer. In this slide, you could see all the three processes. This is the silicon wafer cross-section view. This is the cross-section view of the silicon wafer on which some structures or devices are made. So this is the silicon wafer. So here you could see that we have made a device on the surface of the silicon wafer. If you make a device on the surface of the silicon wafer, that process or technique is known as surface micromachining. However, if you make a device within the silicon wafer by etching inside the silicon wafer, and that structure is that process is known as bulk micromachining. Whereas in microforming, first we make a mold on the silicon substrate, and then in the mold we do electroplating. Electroplating is done. So that process is microforming. So by these three fabrication techniques, normally we could fabricate MEMS. Why normally for the MEMS fabrication, silicon is used. The MEMS initially when it is originated, it was or now still it is a silicon based processing technology. Silicon based processing technology means the main material is silicon. The wafer material on which the devices are made is silicon. Such a process technology is known as silicon based technology. So why we are using silicon for the fabrication of MEMS, or why silicon technology is used? Number one, silicon is abundant and inexpensive. Silicon is abundantly available and it is inexpensive. Billions invested in developing pure wafer and silicon processes. As we discussed in the last lecture, that initially the microelectronics is developed in the 1960s, and afterwards the MEMS originated from the microelectronics. The microelectronics technology was based, it's still based on the silicon processing technology. So therefore, already we have the technology, so we utilize the same technology and we started making MEMS with that silicon processing technology. And native oxide with good electrical properties. Silicon is the material which could make native oxide, and those native oxides could have very good electrical properties. It is well understood, well known. Because of all these three reasons, normally silicon is used as the main material for the substrate for the MEMS device. Materials traditionally MEMS have been fabricated using the same materials used in silicon-based microelectronics. This is what we will concentrate on. We have crystalline silicon, that is single crystal silicon, polycrystalline silicon, which is generally known as polysilicon. We have oxides of silicon, polycrystalline or amorphous dielectric layers, and we have metal films. So these are the materials which are actually available for the manufacturing of MEMS processes. Here on the slide, you also see the silicon wafer. So this is a silicon wafer. Here you see silicon wafers of different diameters. The silicon wafers are available in different diameters and in different thicknesses. So depending upon the user or inventor or scientists or researchers, normally they have to buy silicon wafers according to their requirement. So single crystal silicon wafers are available. Poly silicon silicon wafers are available. Silicon wafers on which there is layer of oxide layer, it is available. Polysilicon with metallization, it is also available. Here on this picture, you see this is the raw silicon. It is used to, it is melted, and actually after melting, we make this ingot, which is known as silicon ingot. It is silicon ingot, and this silicon ingot is then sliced. It is sliced into wafers. It is first with the diamond saw, we slice this silicon ingot and we make silicon wafer. And then these silicon wafers are polished to mirror surfaces. So after polishing to mirror surfaces in different thicknesses and in different diameters, they are available for sale in the market. Silicon crystal structure, it is diamond or equivalently to interpenetrating FCC space center cube lattices by A by 4 along. This is the crystal structure of a silicon material. So it is FFC structure, and you could see that this is the silicon crystalline structure, lattice structure. A is the lattice aspect for silicon A. A is this dimension, the side length of the cubic crystal of the silicon, and it is 5.43 Armstrong at 300 Kelvin. Normally in silicon, we define the crystalline plane. So this is the coordinates. If this is the Cartesian coordinate system, this is x-axis, this is y-axis, this is z-axis, and this is the silicon crystal. And if you are defining this plane for this silicon crystal, so for the plane definition, normally you may have learned or studied this in the chemistry. We use Miller indices. So specific plane, this is the notation for the specific plane. We use parentheses for the specific plane, and these are the Miller indices HKL. And set of equivalent or similar planes are represented by the brasses bracket. And specific direction is notified or denoted by square bracket. Parallel to normal plane and set of equivalent directions. If you have too many equivalent directions, so it is represented by this form. Miller index normally this is the Miller index for each coordinate, and it is the reciprocal of the value. It is the reciprocal of the value where the plane is cutting the axis. For example, if you look here, if you consider this plane, so this plane is intersecting. This is a unit crystal structure. Lattice structure is a unit cell. So each side is one. Each side of this unit cell or crystal is one. So if you look at this plane, so it is cutting x-axis, at 1 because this length is 1. And for the Miller index, we have to take the reciprocal of this value, that is the plane where the plane is cutting the axis. So the reciprocal of 1 is 1 by 1. And if you look at this plane, it is not intersecting y-axis and it is not intersecting z-axis. So at which point it is cutting y-axis infinity. It is not cutting, so we could say that infinity. So infinity is the reciprocal of infinity, 1 over infinity. And similarly, the reciprocal of infinity for z-axis is 1 over infinity. So 1 comes from here. So this Miller index is 1. For x-axis it is 1. For y-axis it is 0. 1 over infinity is 0. Similarly, 1 over infinity is 0. So the Miller index for this plane is 1, 0, 0. Similarly, if we look at this plane, the red line represented by the red line, it is intersecting the x-axis at 1. So the reciprocal of that would be the Miller index, so 1 by 1. It is intersecting y-axis at 1. So the reciprocal of this is 1 by 1. And similarly, z 1. So 1 by 1 is 1. So the Miller index, or Miller indices for this plane, the red color represented by the red color, it is 1, 1, 1. So normally we identify the silicon wafer by the plane which is located at the top surface of the silicon wafer. So normally silicon wafers, when we buy silicon wafers, so the first question normally that we ask is that it is whether it is single crystal silicon or polysilicon. So if it is single crystal silicon wafer, then we have to ask, so what is the plane on the top surface of the silicon wafer, whether it is 1, 0, 0, 1, 1, 1, or 1, 1, 0, etc. Because that is normally important when we are doing the bulk micromachining. Materials that are available for the MEMS fabrication. Remember that in microelectronics and MEMS and MEMS, not too much materials are available to us. So not too many options are available with us. There are a number of very small amount of materials which could be utilized and we could do fabrication of the MEMS and microelectronics to that. In large scale domain, a large amount of materials are available to do fabrication, but that is not the case with the microelectronics and MEMS. We are limited. We are limited by a very small amount of material. So, silicon wafers which are available normally, which are used silicon wafers which are used silicon, gallium, sorry, germanium, and gallium arsenide. So these are the three wafers which are normally used for the fabrication of microelectronics and MEMS. And here you could see the physical properties. These are the physical properties: atomic weight, density, um, atomic density, lattice constant, that is A, for silicon, germanium, gallium arsenide. These are the thermal properties of these wafers, and these are the electrical properties. So these are the three normally materials from which we use, from which we normally make wafers, and those wafers are available in the market. So depending upon the requirement, first you have to select a specific type of wafer, whether you need silicon wafer, germanium wafer, or gallium arsenide wafer. In this table, you could see the materials which normally we use for the fabrication of MEMS: aluminium, molybdenum, stainless steel, tungsten, steel, silicon, silicon dioxide, iron, silicon nitride, aluminum oxide, titanium carbide, silicon carbide. And so some properties, mechanical properties and thermal properties are given. Heat strength, smooth hardness, Young's modulus, density, thermal conductivity, thermal expansion coefficient. So normally these tables are important when you are doing the designing of your device, because normally before fabrication you have to think what layer of material you have to add it to the silicon wafer, from which layers of material you have to make your device. Uh, the layers which you are adding, what is the thermal expansion coefficient? That is very important, because normally during fabrication you have to subject the wafer or the previous layer to temperature gradients, and because of that temperature gradient, the material would expand. And if there is too much difference between the thermal expansion coefficient of the adjacent layers, then the residual stresses will be produced inside the layers, which could destroy your whole process of fabrication. Some more tables. As I discussed with you that these tables are important. You have to consult these tables before or during the design phase of your device, at which layer you have to add or which materials you have to add. So these are very important, and you have to go through those books or papers, or you have to look for these tables and find out these values or etc. which need, for example, the Young's modulus, uh, coefficient of thermal expansion, etc. So this is the table for the silicon, gallium arsenide, silicon dioxide, which is normally added on top of the silicon wafer, and silicon nitride. Normally these two are used as a dielectric layers on top of the silicon wafer in order to thermally, in order to electrically isolate the silicon wafer when we fabricate. So the physical properties, mechanical properties, and thermal properties of these are given in this. Similarly, the materials that we added as thin film on top of the silicon wafer, aluminium, gold, silver, chromium, titanium, tungsten, etc. So here you find out the physical properties, thermal properties, and the mechanical properties of those materials. Some important properties of active material used in microsensors. So as you could see that we don't have too much options for the materials which could be used to fabricate maps. So very few materials are available to do that fabrication. So primary micromachining substrates, elemental semiconductors, group 4. So we have silicon and germanium material from which the silicon wafers are made. Compound semiconductors, group 3 and 5, gallium arsenide, indium phosphide. So these are the materials from which you could make compound semiconductor wafers, and non-semiconductor substrates which are available are quartz and sphere. These are the glass substrates. So normally glass substrates are available. Single element wafers such as silicon and germanium that are available, and compound semiconductors gallium arsenide and indium phosphate. Those are available in the market. Uh, Normally, before fabrication, you have to decide about the substrate or wafer on top of which you have to fabricate your MEMS device. The glass substrates are cheap. They are low cost. However, it is glass is electrically insulated material, so you have to keep that in mind. Similarly, before the fabrication, you have to decide which wafer would be more suitable for your device. You have to decide that well before the fabrication. Microelectronics or non fabrication. So the first step is the silicon wafer. You need a wafer. Uh, First step is after you have the silicon wafer, you have to prepare the silicon wafer. You have to clean the silicon wafer. The wafer which you would buy from the market would be not clean. It would have dust, dirt, grease, and oil particles. So you have to clean your silicon wafer. So there is a standard procedure for the silicon wafer cleaning, which is known as RCA1 and RCA2. So you have to look at the recipe by which you have to clean the silicon wafer. So first you have to wash your silicon wafer with isopropanol, then you have to rinse with the DI water, and then you have to dry with the nitrogen gas. So after cleaning the silicon wafer, then film formation. You have to deposit the thin film on top of the silicon wafer. So before the fabrication, you have to decide which layer you have to add it on the silicon wafer. So that process is known as thin film deposition. So thin film deposition is done. After thin film deposition on top of the silicon wafer, and this thin film deposition is done by evaporation or by sputtering, etc. Annealing is performed. Annealing, because this is silicon wafer, it could have different coefficient of thermal expansion, and on top of it, you have added a thin film of different materials such as aluminium or gold or chromium or copper, etc. And that material has a different coefficient of thermal expansion. So normally there would be residual stresses in that deposited layer. So in order to remove that residual stresses, we perform annealing. Annealing, what we do in the annealing, you have to put the wafer inside the furnace. You have to heat the wafer to a specific temperature, and then you have to shut down the furnace and allow the wafer to cool down to room temperature. This process is known as annealing. And due to this annealing process, the residual stresses which would be produced because of the difference due to the difference between the coefficient of thermal expansion between two adjacent layers of different materials, that would be removed. And after that, you have to go back, and we have to add pattern to the substrate. We have added a thin film, so next we have to add features. Which feature you want to make on the substrate, which surface or area of the thin film you want to add. So for that, actually, you have to add a mask on top of the silicon wafer. So we use photolithography to transfer the pattern from the mask. So this is the mask. Here you see the mask. On the mask, mask is normally made of glass, and these masks are manufactured outside. you will not manufacture these by yourself. So there are companies or organizations which are making masks for you, computer programs such as Coventovir or MEMS Pro, Alagate. You have to make the layout of your features in the computer program, and you have to send that files to the mask manufacturer, and they would manufacture the mask. So on the mask, you would have to, which you want to make, or shapes which you want to make on the device, or the shapes of features which you want to transfer to the substrate, and that would be done with the photolithography. We will study this photolithography in detail, but just remember that with photolithography, the features on the mask is transferred to the substrate. Afterwards, you have to do the doping. You have to change the properties. Doping it also depends whether you want doping inside the material or not. So that also depends upon the device or your process sequence. Uh, Doping is required, so in between photolithography and here you will be doing doping. After doping, you have to do annealing, and after annealing, if you want to add another layer and then you doping, so that would be all done. After photolithography, when the mask of photoresist is added to the substrate, we do etching. Etching will be done. Etching is, by etching we mean selective etching. We would remove the material which is exposed to the etchant solution. So we have to remove some portion of the added layer of metal on top of the silicon wafer in order to make a shape of structure on top of the silicon wafer. So when that etching is performed, uh, then after that etching again, if you want to add another layer, you have to send your wafer back to the surface preparation. After surface preparation, again we have to add another layer of the material, and we have to repeat all these processes again. Etching. If you want to add another layer, again you have to send your wafer here. You have to prepare the surface. You have to add a layer by deposition, perform annealing, photolithography, and then etching. So surface by surface, we would, or layer by layer, we would make the MEMS device. So in this way, layer by layer, you have to make your MEMS device. And once the devices are made ready,